So I'll be presenting the algorithm for astronomical high contrast imaging of circumstellar disks, and I will compare two kinds of approach, inverse problem, like Mustard inverse problem, and the PCA-based methods. So high contrast imaging, it's the art of observing very faint objects that are just next to stars. So not only we need like super good resolutions, but also we have a problem is that the star is on. So we are basically trying to observe a small pile of light just next to a lighthouse. The planet is completely drawn into the halo of the star. The flux of that like we come from the star and the planets, they huge flux ratios or high contrast imaging. So to make this possible, we need like a lot of fancy instrument, and the key instrument here, it's the chronograph. This is the instrument that will basically hide or cancel at best the lights that come from the star to reveal the faint circumstellar signal that is hidden around. The problem is that the instrument is not perfect, and the images will be corrupted with what we call the speckle. So basically, those are stellar light leakage that come from the imperfection of the instrument, and they can be like as bright or brighter than the signal of interest. So we will need to remove them if we want to discover planets or this. And so to do that, we will have the help of observing strategy so that we will be able to distinguish speckles from signal with the post-processing. So one of the most commonly used observing strategy for infrared or near infrared, it's the angular differential imaging. So basically, the pupil will be fixed on the detector. So through the night, the field of view will rotate, and so with the particle. And so the outputs at it's a sequences of images where our circumstellar disk or planets will rotate with a known angle, and the speckle field will remain more or less static. I'll make just a small parenthesis to just tell you what is the system that you're observing, and that I'll continue for the processing stuff. So this system here, it's PCA-17. It's an absolutely unique system because it's a protoplanetary disk, so very young disk. We have also two detection of planets in this one, and on top of this, we have a circumplanetary disk around planet B. So this is like a super like famous like study to death system. But anyway, end of the parenthesis. So to process those data sets, the two more commonly used techniques nowadays is the principal component analysis, PCA, or the median subtraction. So they are great for detecting planets, they work well, but as you can see, for extended signal, it will introduce systematical deformation, and so that can be the interpretation of the experiment. Because of this, recently, many algorithms have been developed specifically to recover extended sources from ADI sequences. So I'm guilty myself. I made one of them. It's Mustard, the one that is just next to me. And so it's an inverse problem approach, as well as two others, so REXPACO and MAYONNAISE. And the two other ones, there are PCA-based methods. So it's the principal component analysis alone and the iterative principal component analysis. So for the average astronomer, the situation raised questions. What can I trust? They all get you some kind of different interpretation of the disk. And if I want to make studies, a pitch angle, flux estimation, I don't know, you want to know what you can trust them all. And so this talk, like the goals of this talk, there is two goals. So the first one is to present the algorithms that have been developing, some we started, and the second one is to review the status of the state or the state of the art algorithms to process ADI sequences. So the first two steps, we will get through the theory of what data we are looking at and the algorithms. The first step, I will present my test pipelines. And at the end, we'll synthesize all our observations and try to understand what's going on. All right, so this is how we are going to proceed for the comparison. I have like a big table, and so each column is one of the algorithms, PCA, IPCA, etc. And so in each cells, I will write down the assumption that each algorithm do on the data set. And so the first column that we are going to fill is the reality, what we actually know about the data. So as we saw in introduction, the ADI dataset is basically the speckle field, the disk signal that is rotating, and the rest, which is the noise. And so what do we know about that? So we know that the quasi-static, like the speckle field have a quasi-static behavior. So it's not going really to be static. It's going to have some kind of stochastic behavior, but it's not, we know that it's going to be highly correlated from one frame to another. The rotating signal, so disks and planets will look like dots, and it's going to be positive. And for the disks, well, disks can have different widths, different shapes. They can have structure like spiral, gaps, shadows, etc. And we want to capture them. And for the noise, so the noise is basically a mix of white noise, shot noise, weekend noise, etc. But actually, we are not that limited by the noise. What's the more bothering us is the variation of the speckle field that we are going to struggle to capture correctly. And another thing that is really bothering us, but it's very common in the data set, is the other phenomenon, nuisance phenomena that happen. A very common one, it's the wind-driven halo. So basically, it's atmospheric turbulences that were uncorrected from our instrument, and it will elongate the the PSF, and it will create that deformation and that kind of butterfly pattern. So this will be annoying. And the last limitation for extended signal, it's the inherent limitation of our observing strategy. We are using the rotation to disentangle speckle from signal. The problem is, like, if you take a disk and you rotate it, then that you can see that there is some of the pixels that will always be within the disk signals for the rotation. So this is the rotation invariant flux. So basically, they will appear static. And so, yeah, they're going to be confused with what we will assign to the speckle field, and it will cause deformation. Yeah. So that's all for the data. Now, how our algorithms are going to deal with this. So now that's the step where we are going to fill the cells. So first, the PCA. So I believe that probably most of you have like kind of an idea of what PCA is. Basically, for images, they are vectors, a bunch of vectors. There's a subspace. We do the SVD decomposition. We have EGI vectors. We make the projection of the principal component, one or more. And basically, that's a good way in practice of estimating something that is common in like for a series of frames. And so that's what we're going to use for our estimation of. And then to get this signal, we remove our estimation of the speckle field. We do the mean. Well, so with this technique, there is not much physical assumption we are going to make. The signal can be negative, even though we know that it's normally positive. There is no assumption in the noise, and since we're basically removing that everything that is static, the flux invariant to the rotation will be removed as well. One great solution to tackle, like as you observe in the introduction, when I show you the pictures, it has the tendency of being super aggressive with the signal and causing like a very big deformation. And one very good idea that people found to tackle this is to the iterative PCA. So basically, we are going to recompute the principal component, but at each iteration, we are going to remove the disk signals that we estimated last step. And basically, that will greatly help for the self-subtraction. So we will recover markers like this. And inside those iterations, we can enforce some physical things like the positivity of the signal, basically. However, we are still removing everything that is static. So the speckle field, the flux invariant to the rotation will always belong to the speckle. Now, the inverse problem approach. Like, so you've seen this equation before, and so I'm not going to talk about it. Inverse problem approach, it kind of look more, credible. Like the credibility, it's important. We want to be sure. And so it looked more credible because there is a model, because it's probabilistic based, but it's not necessarily that true because it depends of how well our model will fit with the reality. And so that's why we're like filling all those cells to see like how good our estimator. Okay. Okay, so we'll start with the first inverse problem approach, REXPACO. So basically, they model the speckle field as static for the frame. And the little particularity of this approach is that they will learn the noise statistic from a patch outside of on the edge of the image where there is no signal of interest, and they will apply it where there is signal. So if you're interested, there is the references. All right, so this is one way of modeling the idea cube. The other models that have been tried is to model the speckle field as unique at its frame. The problem is it's a bit unconstrained, so they needed a constraint, and for that they used the iterative PCA. What this model is really good at, though, it's because they also add the PSF deconvolution, so they make the deconvolution, and it works very great with the they use like the shell-it as a constraint to make it like a clean, pretty image of the deconvolved disk. All right, and so the last approach, so it's mine, it's Mustar. So I have the same model as REXPACO, but so my goal was I witnessed that like the flux of invariant rotation were systematically removed from all of our algorithms. So I tried to have some kind of solution for that. And so the idea that I have is to add a prior on add a prior for like sorting that flux invariant rotation. So basically it will use this mask, which is a Gaussian, which should represent the way the stellar halo will spread along on the frame. And so to show you what it's kind of doing in practice. If you here and this is the iterative PCA. So what you can see is that the speckle field estimate, you can see that there is kind of a circle of light. So this is flux invariant to the rotation that's been assigned to the. And so this circle of line, it matches with some shadows in the disk that you can witness. So this is a signpost of flux invariant to the rotation that is missing. And with the Gaussian prior, we kind of make the speckle field estimator more looking like this. And so we remove the, it's not perfect, but we have some other interpretation of the disk where we don't see the signpost of flux invariant to the rotation. All right. So now that the theory is in one extent. So that's where we do the tests. So I only tested 3 algorithms. These are the ones that I mastered. So the PCA, the iterative PCA, which is grids, which is the implementation that I expected from the MAYONNAISE pipeline, and the Mustar algorithm. And so for my tests, I used observation of stars where I know there is no disk on planets around. I simulated different kind of morphology of disks, and I injected in them with different flux ratio. And then I tested my 3 algorithms on them. The output that I got is that table. So this is the cube on the collector. And the color of each cells tell you which algorithm performs the best according to the SIM metric. So I've noticed that people use sim here very commonly, but for us it's not that common. So we questioned like, why is the sim metric? And so if I change the metrics, does it change my results? And it turns out that yes, changing the metrics cannot change the results of what the table will look like. So basically, what it's going to do is that no metric is really perfect, and they all gonna kind of like capture some information. For example, the Spearman metrics, it will be better to tell me the structure of the disk is globally more restored, but it's not going to be very sensitive to residual, where other metrics will be more sensitive to that. It's important because sometimes I will see that the same metric will tell me, yes, PCI is better, but when I look at it, I'm like, yeah, there is more residual, it's not sparse, but the structure is better. So, well, since there is not really like perfect metrics, what we've noticed is that when all the metrics agrees, that means the disk is ambiguously restored better by one algorithm than another. So I also add little black stars, which is like all is the sample that algorithm perform, and ambiguously those are the results. So we like make the synthesis and try to understand what's going on. Observations, it's well, I show that but there's still some kind of trend, and the trend is would be better to like bright disks, and for disks have lots of flux invariant rotation. Iterative PCA is globally like more better everywhere results. And so here is some example when there is lots of flux invariant rotation, it will help have a better morphology, but you'll see that there's more residual in the image in general. So yeah, this is some example. And yeah. But as you can see, there is the residuals, and overall on all the data set, the iterative PCA is better. And so this can be explained by the adequacy issues we have with our model and the reality. Modeling the speckles as static can be a problem for plain disk, as the variation of the speckles will average out, so it will not work very well. And also the Gaussian mice that I'm using, it's not a very good prior. I mean, it works somehow, but it's not perfectly realistic. And so last observations, overall grid is more often selected as the best estimation, and it's also totals the most of black stars, so an ambiguously better estimation. Yes, so if you forget about the inverse plane approach and you just look at the improvement between the PCA and the active PCA, it's significant. It really helps having a better disk, even though it doesn't correct for the flux invariant rotation. So this is two examples. So conclusion based on this analysis, what algorithm should I recommend to an astronomer to use for their data set? So what I will recommend for an astronomer is to use the iterative PCA in most cases, or at least as first attempt, because it's like for its combined robustness, performance, and practice stability, which is not something that we like talk into the table, but this is an algorithm that is fast, easy to use compared to inverse Scrum approach. So yep. But it's not the best all the time, and there can be deformation, and like if you have like one data set that you really want to analyze and you know that it matches the scope of validity of the algorithms, you can try a more sophisticated methods to have a better interpretation of what the flux invariant rotation can be. And so for my future works, so I'm still trying to solve the problem of flux invariant rotation, but in a more trustful way. So at the opposite that everybody seems to be doing here. I wanted to have more information, more data. So I used I included reference to our libraries who have a better prior on the speckle field. So I can use that for both improve the inverse problem approach or the iterative PCA. And for the iterative PCA, I already have a result that seems pretty good. So this is the iterative PCA alone and the iterative PCA with the reference source. And as you can see, the flux invariant to the rotation is solved. For the inverse problem approach with the reference library, it's not very good. So yes, if you have like, if you're a specialist of some kind and you have some suggestion to me for improvement, so yeah, don't go at me, and thank you.
Okay, time for some questions. Yes, please.
Thanks for your interesting talk. So I'm not an astronomer, so sorry if it's a naive question, but why the disks look really dark in the middle? Yeah, I mean, why it looks really dark in the middle? And the other thing is, this looks to a layman like a gravitational lens. So is this, I mean, like light coming through some kind of space deformation because of black hole and so on. So is this a kind of a background or a significant background to your signal? I mean, if you look at the left picture, yes. Okay. I mean, this one or this one?
Region of the center is not selected, so we have this not included here. And the black here is here, and because like at the tendency of like making this area
Partially, but I mean, on the left side, this picture, doesn't it look like gravitational lensing somehow? Okay, maybe not.
Sorry. Okay. No. This is atmospheric turbulences. Or this is like a variation of the speckle field that we aren't captured correctly. That's all.
Okay, so thank you. Very interesting slides and talk. I was wondering if you could tell a little bit more about the Gaussian masking, Gaussian weighting you explained that solved this ambiguity due to the rotation.
Yes. So okay. So this is quite approximative, to be honest. This is just like at visualization, we'll put all the flux invariant to the rotation in the disk estimate. Wait. And then we will we'll push that flux invariant to the rotation according to the mask till we end our minimization, and that's how we will sort it. But we will need to define the width of the Gaussian and the overall shape. And so yes, that will influence the way our estimation will be. This is not perfect. This is like an interpretation. So basically the goal of the Gaussian is to represent these things here, the speckle field and the stellar halo that's spreading, but this is not perfect because there is no really function that really described it correctly. That the Gaussian is that one function that somehow will be fitted a little bit, and that's the best we can do, so that's okay.
We are all using Gaussian anyway, so.
Yeah.
Any other question? Let's talk
sometimes in difference, which kind of where you fraction the image into different annuli, like a Gaussian mask, or
What phenomena exactly?
so sometimes these algorithms, they have annular versions.
Annual what?
Annular version of the algorithm where you always take just a
Yes,
part of the
annual,
image.
yes.
So I guess you don't do that here.
No.
So is
Which
it because you use this Gaussian mask to rescale things, or is it related to the Gaussian mask?
I mean, I think it's not because of the Gaussian mask. We can like cut the Gaussian mask as well, but it's just like we do full frame, and it's like, I mean, there's not really point. I mean, when they do annular stuff, like for example, for the PCA, it's to like having a better, like, you know, here, I don't think it's really applied. That I don't think it's really like, well, maybe because that's, yeah.
Okay. Any other question? In that case, I have a quick one. So it seems that PCA is very much popular. It's really PCA and PCA. May I ask why the community thinks that orthogonality between components is a good thing? Why not just going to something like ICA, which is independent components, statistically independent components, but they are not orthogonal? Is there any leg for this idea of just getting away from the orthogonality of components?
So there is people that are trying to find the best way of doing the PCA and stuff. I think it's just that like I believe that it's just the first thing that they found, and it works in practice, so we keep it. But yeah, people are constantly trying to find that. Maybe like if you have the idea and you think in school, like tell me and I will tell other people so they can try.
Yeah, I mean, ICA was very much successful. I don't know, 10 years ago, but that's possibly another direction to check. If there is no other question, please. Oh, you have one. Please, a quick one.
So as far as I understand, these are rotational images, right? Do people consider rotational basis or steerable PCA for the decompositions?
On what?
So as far as I understand from the images, these are rotated images of the same object. So do you consider rotational basis or steerable PCA?
In the PCA, do we have the rotation?
Yeah.
So basically, no, not in the PCA, but it's like, I mean, we're removing the speckle field as static, and then the rotation, it's like when we get this signal, we rotate, we remove the estimation, we rotate the curve, we have our answer. The rotation is leveraged at this stage.
Okay. Thanks.
Okay, thank you very much. For the sake of time, if you have any other question, please keep it and just ask offline. So thank you very much for this interesting talk.